Okay, so let's look at filtering on the STM32. We are going to implement a second order canonical filter, a BiQuad. It's difference equation. So the in this particular equation, the A0 coefficient is over here. We could write A0 for completeness, but we're going to assume the A0 coefficient in this case is 1. If we think about this from, if we transform this from the time domain to a discrete frequency domain, we'd end up with the equation YZ So you may see this in text in either format. When we look at the code, we're going to implement this particular difference equation. Now, in terms of calculation of these coefficients, it really varies depending on the filter that you're going to implement. There are many different filter coefficient calculators that are available. The one that I'm going to just show you has come from the DAFX book. This book here, DAFX Digital Audio Effects, 2nd edition. Fantastic book by Udo Zolzer. Highly recommend it really if you're thinking about looking into digital audio effects. So in the filters and delays section, you will see a section that's all to do with the calculation of different coefficients. Here we have the filter that we're going to implement in our STM32. It's on page 55, and because it's a peaking filter, we calculate the coefficient slightly differently, whether we want a boost or a cut. So these, if you want to refer the code to the actual equations, and indeed if you want to change the filter type, then I'd highly recommend this book. There are many different filter types for you to implement. The way our code is going to be run, we have our audio subsystem, and we are running FreeRTOS. So FreeRTOS code. In there we have, I've set the code up to have a number of tasks or threads. One particular thread is the touch panel thread. The other thread is our audio processing thread, or at least a thread that calls the audio processor. So it's this touch panel which is reading in the coefficients and editing the coefficient values. So that I'll show you the code that changes both the frequency and gain of the filter. So this is going to change the cutoff and the gain, and then the audio process is going to call a function to implement our filter based upon these coefficients. So if we look in FreeRTOS, you'll see we've got a start audio task. This is one of the threads. Obviously you can call that whatever you like. I've called it start audio task. It calls our buffer handling. Buffer handling in this case is the bit of code that receives a message from the interrupt service routines that run when an audio transfer, when the serial audio interface is transferred in half a block of audio samples and then a full block of audio samples. It calls then a function called copy buffer, which copies the audio into our playback buffers and recording buffers for our audio processing element. Look back at previous videos for an outline of that process. Then we've got our OGS task. This is where we do the touch detection. So down here, what I'm doing is I've just created two coefficients, coefficient 1 and coefficient 2. Coefficient 1 is the coefficient that I'm going to utilize based upon the location of the finger on the touch panel. I create a coefficient that goes between the value that represents -12 to +12, and this is in decibels. As we'll see in the audio object, the class that I create, we convert that from dBs into essentially a voltage gain. So then we've got coefficient 2 here. Depending on the value, the coef 2 is going to go between 0 and 1. So this will go between 0 and 2000. So I can scale the touch panel for the frequency range that I want. And then I'm just putting this little +100 here as an end stop. If I take my finger all the way over to the left, the lowest frequency that I can get to is 100 Hertz. And then I call this function update objects. Update objects is just a function that has been created in audio process HPP. This allows us to get CPP function calls, so C++ functions accessible from within the C context of FreeRTOS. So if we have a little look at update objects, we'll see that update objects exists in audio process, and I call my filter object. One of the methods is update coefficients, and I pass it coef1 and coef2. As we'll see when we look at the definitions, I've created two of those objects, one to handle the left channel and one to handle the right channel. So then in audio process, this is where we actually call or pass in the value, the single sample value, into the filter, and we get a processed or filtered audio sample out into audio out. This code here is simply just to convert the floating point value back into a fixed point value to go back in the buffer to be sent back out again. This here is likewise is converting the int16 to a float. So that is just simply performed by this code here. So I fixed my sample rate at 48 kilohertz. When you're creating your coefficients, you have to take the sample rate into account, and as we'll see in the audio object, the audio class itself, that's what we do. So let's look at the header file for the filter. So I've just created this constant filter order. This is just if I wanted to create a larger order filter, I could do, and just makes it a bit more flexible. You could hard code this as a 2 if you wanted to. So what I've got is protected variables. I just have gain in dB, filter cutoff Q, and FS, which is the sample rate of the system. I have my BN, these are my feed forward coefficients, and my AN, these are my feedback coefficients. And then I have two floating point stores, if you like. So these are my filter buffers. I've got X of N, so they're the incoming samples, and then of course sort of X of N1 is going to be the sample delayed by 1, xn2 is sample delayed by 2, etc. Same for the y of n's. I have a constructor, IR block. I have two functions or methods. One is called update coefficients and the other is called process. And that's it, simple as that for the header file. So let's look at the actual implementation in the class. So this is the constructor. I just have default values, gain, the cutoff, etc. And I call update coefficients just to get the filter ready so that there are valid coefficients in the filter upon its creation. So the update coefficients, as I've said, we're coming from page 55, table 2.4 of the DAFX Zolzer book. So we pass in the gain to gain dB, frequency to the cutoff. We calculate the K values and the linear value of the voltage gain. Now, if we look back, we'll see that there are two different tables. We have to normalize differently depending on the A0 coefficient that gets calculated. We normalize differently whether it's a boost or a cut. So that's what these two lines of code are doing here. So see, we've got for a boost, we are just dividing by 1 plus 1 over the Q. So we've got 1 plus 1 over the Q times by K plus K squared, which is what we're doing here. So we just have a if else. We create the BN coefficients here and the AN coefficients according to the table, and then we do the cuts. So this A0 coefficient we're just defining as 1 because it would have been the A0 or AN0 divided by AN0, which means we're going to get a 1. So if we look at the process function now, so there are more efficient ways of coding this. We could use pointers and circular buffers, etc. But this is kind of a brute force filtering method. It should operate fairly quickly, certainly fast enough for real time. So the first thing we do here is implement our buffering. So x of n becomes x of n minus 1, x of n minus 1 becomes x of n minus 2, y of n becomes y of n minus 1, and y of n minus 1 becomes y of n minus 2, etc. Obviously we could implement this using circular buffers, We could use pointers, etc., just to speed everything up, but I'm just keeping this fairly simple at the moment. Here we pass in the floating point sample into x of n0. We zero the current output because we're going to recalculate a new output based on the difference equation. And this is the implementation of the difference equation. So what we do is we do the feed forward coefficients first, b of n, 0 multiplied by x of n0 added to the b of 1 and the b of 2, etc. And then when I steps beyond 0, because we're not dealing with the a0 coefficient, so we're just doing the a1 term and the a2 terms. By that I mean an1 and an2. So we're taking those values away from the rolling summation. Then we're just returning the value yn. So this is the processed audio sample. I've just left this bit of code in here. If you did have an an coefficient, then we would divide the yn down, but obviously that would change the coefficient calculation normalization that we'd done previously. And that is the implementation of the process. So if we look back now at audio process and how we use that filter class, at the start of audio process I've included the header file for the basic filter that we created. So I've instantiated two objects of that class, one to handle the left samples and one to handle the right samples. Within update objects I'm calling the update coefficients method of that object. So coef1 and coef2 are being passed to it. That will be the gain and the frequency that we looked at earlier. And within audio process, we are processing in a block of audio samples, and we're hopping over left and then right and then left and then right. So we do with the left sample first. The left sample gets converted into a float, and we then pass it to the filter object using its process method, and we get a processed sample out. We then convert it back into an int16 and place it back into the playback buffer, and we do the same again for the right sample. And that's it.